In this video, I want to formalize the idea of a vector space looking like Rn. In front of us, we have a graphical representation of the vector space that consists of the set of solutions to the linear equation x minus 3y plus 2z equals 0. As we've discussed, the set of solutions to any linear system is a subspace of Rn, where n is the number of variables. In this case, we have 3 variables, so this is a subspace of R3. And when we look at this graph, it's a plane in R3, and it's reasonable to say that this plane looks like R2. It's just at a different angle, right? And we want to formalize that idea. Similarly, we've said this for other vector spaces that don't even live inside of Rn. So P3, the set of polynomials of degree 3 or less with real coefficients, this is a vector space. And we said that this kind of looks like R4 in the sense that if we take some vector, vectors in P3 being polynomials, so if we take, for instance, the polynomial x cubed minus x plus 5, we want to say, look, we can really associate this with the vector of coefficients of this polynomial. Seems like a natural thing to do. All right, so what we want to do in this video is formalize this idea so that we're not just kind of waving our hands around in different situations saying that things look like Rn, because hopefully these two examples give you this feeling that there are different ways in which a vector space can look like Rn, at least the way we've seen it. V looks like Rn in the sense that when we graph it, we get this plane living in 3-dimensional space, and P3 looks like Rn in that we kind of see a natural way to associate polynomials with vectors. It's not the same thing. So first, some terminology, this notion of isomorphism. We say that V, instead of saying it looks like R2, because that's really kind of vague, non-committal language, we say that V is isomorphic to R2 as a vector space, and I'll explain why I'm adding this qualifier to the end in a second. And similarly, we say that P3 is isomorphic to R4 as a vector space. So what do I mean by that? Well, it's important to realize we're saying that these look like or are isomorphic to these Rn's in the sense that the vector space properties of them are the same. So what I mean by that, for example, is in P3, if I take this polynomial we've already talked about, x cubed minus x plus 5, and I add another polynomial in P3, we get another polynomial. This is a vector space operation, right? I can add 2 polynomials. And if we think about these as living inside of R4 instead, and so we said, well, this would be this vector, and this would be this vector, right? They're just the vectors of coefficients. When we add these 2 vectors, we get 1, 1, 1, 6, which is exactly what we would have associated with the polynomial that we got up there. So we're saying they're isomorphic as vector spaces in that doing addition in one versus addition in the other accomplishes the same thing. Similarly for scalar multiplication, right? If I multiplied a polynomial by a scalar and then did the same thing with its vector representation, everything would line up. The reason we need this qualifier, though, is that P3 is a good example of this. Polynomials can be thought of beyond just vector spaces, right? If I have a polynomial of degree 3, for instance, I could take its derivative and get another polynomial of degree 3 or less. And that's something that I can't do with vectors, right? I can't take a derivative. I can also plug in values for x, right? I can't really do that with a vector. And so P3 has all of this additional structure that R4 doesn't have, and R4 also has structure that P3 doesn't have. We'll talk eventually about how R4 we can think of distances and angles between vectors, I don't know what it means to have a distance between polynomials. So we're really just talking about the addition and scalar multiplication properties when we talk about them being isomorphic, them being the same. Okay, so this idea of isomorphism, where we have a bunch of different things that look different, but it turns out they all can be described by some much smaller collection of things, right? We have all of these vector spaces that on their face look different, but in the end, actually, they're really just Rn kind of in disguise. This notion of isomorphism is fundamental to mathematics. It allows us to study lots of different things, not by individually studying them, but by studying a single thing and then taking what we've learned there and transporting that knowledge to other settings. And this is why in this course we spend so much time working with Rn. It's not just because it's easier to work with, it's because it's easier to work with and we can take what we learned there and very naturally apply it to other settings. So we study Rn, then all of a sudden we can say stuff about polynomials, or we can say stuff about these subspaces of solution sets. Okay, so I want to introduce some notation here because I have some terminology here, P3 being isomorphic to R4, but I want to specify exactly how I'm thinking of these vector spaces as isomorphic, how I'm thinking of them as the same, and I need some notation. And I want you to bear with me on this initial definition. I'm going to define something, and if you understand what it means, then I am very impressed, because it's one of those definitions that you need to work with, I think, to understand it. I'll quickly define it, give you a chance to look at it, and then I'll move on to some examples, because that's how you'll ultimately understand it. Okay, so we have an n-dimensional vector space V. We haven't officially defined dimension, but it really just means that V has a basis with n elements. So we have a vector space, a basis, and we have some vector in that space. Since this is a basis, it means that there's exactly one way to write our vector as a linear combination of the basis vectors. We'll define rep B of V to be the vector of coefficients in the linear combination expression in terms of the basis elements. So we write V in terms of our basis elements, and rep B of V is just those coefficients. Let's move away from this definition. It's too confusing. Let's go back to our set of solutions. Actually, let's not. Let's move somewhere where it's even a little simpler. In P3, I think it's actually very straightforward to see how this works. It may take a little bit to wrap your head around it, but there's not any work we need to do anyway. Here, the basis that I want to use, and the order matters. If I switch the order, it would switch the order of the entries in the vector, is this. This is a pretty standard basis to use for P3. And what I'm saying is that if I have this vector, x cubed minus x plus 3, what I want to do, this is my vector V, then rep B of V is the vector of coefficients. Well, the coefficient of x cubed is 1. The coefficient of x squared is 0. The coefficient of x is -1. And the constant term is 3. That's my representation. So this is exactly what we previously did, right? It's not different. It's just using new notation and new terminology. But it's formalizing, right? So we're not waving our hands at it. We're saying, no, this is what we're literally doing. We're taking a basis that we're considering to have an order. We're looking at the coefficients when we write this in terms of our basis, and our representation is the vector of coefficients. Let's move up to here, to the set of solutions to this linear equation. And it's going to be a little cramped, so I can fit it all on the screen. We need a basis for this first. And so I'll just give you a basis. We know how to find a basis for this, right? This is the process of solving a linear system, right? When we solve a linear equation, that gives us a basis for the space of solutions, but I don't want to do that in this video. So quickly, just what are these vectors on the screen? The red vector I'll call V1. Let's make sure we can actually see this. as I said, a little bit cramped. v1 is going to be the vector 3, 1, 0. This orange vector is the vector -2, 0, 1. And this is the basis for V. And so that's the basis I'm going to use. Forgot my little arrows here. Now let's put a third vector on the screen. This green vector that I'll call U. And this vector is the vector, I'm going to move away from the screen in a second so I have space and it's not too cramped, is the vector -1, 1, 2. So let's move away from this screen. I want to represent this vector with respect to the basis v1 and v2. And in order to do that, I'll notice that this vector is v1 plus 2v2. And that means that rep b of u is the vector 1, 2. Because 1 is the coefficient of v1, 2 is the coefficient of v2, and that's the basis we're considering these representations with respect to. So I've represented this vector u as a vector in R2. So this is nice because it really kind of solidifies what we mean when we say that this vector space looks like R2. We're saying, look, we have a way of associating every single vector in this vector space with a different vector in R2. They each are associated with a unique vector. And addition works the same way. Scalar multiplication works the same way in this space or in R2. So we've taken these vectors inside R3, noticed that they all live in the same two-dimensional plane, and given this sort of R2 structure to it with this rep B thing. So two final things to note. One really important thing. The choice of basis matters. You can choose an infinite number of different bases for any vector space, and a different basis will give you a different representation. So choice of basis matters. Sometimes there are kind of obvious choices of basis, right? Like, going the wrong way here. This is a relatively natural choice of basis for P3. Sometimes, as in this example, this is the sort of basis you would often end up with just by solving a linear system, but there's not some natural choice of basis. In any case, everything will work no matter what basis you choose, but you'll get different answers. You just have to be consistent and always represent with the same basis. The final note I want to make is that this notation is not actually that standard. It's the notation that our textbook uses, and the author mentions this in the textbook, and he points out, and I agree with him, that even though it's not standard, the more standard notation that we're not going to introduce is a little too subtle. It doesn't really emphasize what's going on. I like this notation in that it really emphasizes that this thing is a function. Right? We don't have to worry too much about that, but we're taking a vector and we're getting a different thing as an output. And because it's kind of written in that way, it's hard to miss, right? Maybe you look at this and you don't know what it means, but it's hard to misinterpret. All right, so I haven't really described how to do a lot of this stuff, right? I kind of waved my hands at this step, or didn't even do that. I just skipped over how I figured this out. In a separate video, I'm going to talk about how we actually use this very abstract concept to solve problems, how we find these representations, calculate things like this, and how we go and use them to answer questions about linear independence, span, and basis.